All right, log functions and their graphs. We're just going to jump into it. That's the natural log function. Okay? It doesn't have to be natural log. It would be log of any base. It looks pretty much the same. So let's pretend that we don't have these in front of us. Can we answer all of them? So what's the domain? Just looking at the graph. What's the domain? 0 to infinity. Does it include 0?
No.
No, that's an asymptote. So we know it has a vertical asymptote at x equals 0. What's the range? All reals, negative infinity to infinity, okay? What is it increasing? Always? Okay. It never decreases. Does it have a max or a min? No. Does it have a horizontal asymptote? No. Is it bounded? Meaning, is there a limit to where it can go? No. It's going to go up, up, up forever. Down, down, down forever. Bounded is talking about range values. Okay. It's bounded. It can't go further left than 0, but that's not technically a bound. If we're talking end behavior, is there a limit as x approaches negative infinity? No, because it doesn't approach negative infinity. So you only have one end behavior. What's the end behavior? Infinity, right? It's going to continue going up. Okay? So you need to know those properties. You should be able to look at the graph and state all those properties. The graph is the key. You need to know what the graph looks like. Nate?
Are limiting behaviors just going to infinity?
End behaviors? No.
So, like, why is it, or limiting, like, why couldn't you have limiting like x as x approaches 0?
Okay, as x approaches 0, that's an asymptotic behavior because you're approaching the asymptote. So that's not an end behavior. Limits, they're all limits, though. You understand what I'm saying? So when it's saying end behavior, there's only one end behavior because there's only one end of the graph. The other one would be an asymptote. So it's asymptotic. Okay? Everyone understand his question? As x approaches 0 from the right, from the little plus, it's going to negative infinity. All right. So that's the natural log function. That's the parent function, if you will.
But what's the boundedness?
The boundedness means it's not bounded. It goes up, up, up forever, and it goes down, down, down forever.
So how would it be if it was bounded?
If it was bounded, if I have, let's say the logistics function that does this, it's bounded above by a horizontal asymptote and below by a horizontal asymptote, so it's stuck. It can't go lower than a number, it can't go higher than a number. Okay, so when you're stuck in between something, it's bounded. All right, so transforming these graphs, guys, is the same as transforming any other function we've talked about. The natural log of x plus 2, how does that change the graph from the natural log of x? It shifts it to the left 2, right? We know this. We have done this over and over again. If it's happening inside the x, it's opposite of what you think. Okay? Let's do this one over here. I am multiplying 3 times outside. So this is a vertical stretch by 3. So just picture the graph. You're just taking it and you're pulling it up. So it goes up higher, quicker, at a faster rate of going up. 2 things are happening here. The 3 is going to move it to the left 3 because it's positive, and you are flipping it horizontally. Okay, over the x-axis. So I moved it. So I was here. I was on this blue graph. So I moved this guy over 1, 2, 3.
I got scared.
A big jump in my recording. Forgot to start. Here we go. Exponentials in logarithms are inverses of each other. So this is the exponential graph. This is the logarithmic graph. Inverses. If you remember how we write inverses, so this is the exponent graph. So its inverse would be x equals b to the y. This is the same thing as the log of bx equals y. These are equivalent, the two pink ones. Okay? This is considered exponential form. This is considered logarithmic form. You're going to have to be able to switch back and forth between the two. That's like key. All right? Very important. So to help us with that, we have Ben the log bunny. Okay? So Ben the log bunny. When he's in exponential form, you have the word Ben, base, exponent equals a number. In logarithmic form, you have bunny. So you have the log with a base b of the number equals e. So that helps you remember, hopefully, the order that you put them in. So Ben and then log bunny. Base, exponent equals a number. The log of the number base equals the exponent. Okay? So you have to be able to convert from one to the other, back and forth. Nate?
What if you weren't given n as like log b? What if you weren't given n and you had to solve for that? How would you do that?
You know, funny you should ask. In a few slides, we're going to go there. We're going to learn it all. Learn it all. Right now, this is just to rewrite in both forms. Okay? So, let's see if you can. Did we write that down? Do we have Ben the log bunny down? You don't have to draw the bunny. It may help you remember, but you don't have to. Ah! Sorry. Okay. So we're going to try a couple. So this is exponential form. So this is your Ben. And we want to put it in the log bunny form. So we're going to have log of the base. The base is just this little baby number of the number equals the exponent. E-N-E. Base, number, exponent. Can we do that? I did that earlier too. I don't know why. Okay. So we're going to have the log. Base is 2. The number is equals the exponent. Easy enough? I mean, it's not hard. You just have to understand how you're going to flip it. So these are in log form, so you have to write it in Ben form. So you need the base, the exponent, number. So base, your E is what it equals, and then your number. So remember, this is your B, bunny. Let's put it in Ben form. So our base here is 5. Exponent is -2. Anytime you have a negative exponent with a base that's bigger than 1, it's going to make it a negative, or not negative, a number less than 1. Okay, so if we all write those, do that. All right. Now, evaluating logs. This is when people get all flustered and like, that's really hard and I don't know how to do that. What's the log of 8 in base 2? Okay, we don't know what it equals, so let's make it equal to x. So all they're asking here is what exponent would you put with a 2 to get an 8? 3. That's the answer. That's all logs are. They're saying what is the exponent that I'd put with this base to get this number? Okay? So since 8 is 2 to the 3rd, it would equal 3. All right? So you do the same thing here. 3 to what power gives me the square root of 3? Yeah. You can rewrite the square root as 3 to the 1/2. So x equals 1/2. Does that make sense? Are we following? Okay. So 5 to what power gives me 1 over 25? Well, 25 is 5 squared, right? How can I make that 5 up top? If I moved him up top, what happens to the exponent when you move him? It becomes negative. So remember yesterday we said if we have a negative exponent, it has to go down. Sometimes we have to make it negative. So the x is going to equal -2. So basically you're wanting to get the base is the same on both sides. You guys try this second one here. Yeah, 4 to what power gives me a 1? 0. Any log of 1, I don't care what base you're in, it's going to be 0. Right? It doesn't matter what this 4 is. The 0 exponent makes it to a 1. So that's a special rule that you can remember. Okay? And then this next one is also a special rule. 7 to what power gives me a 7? 1. So anytime you're taking the log of the number that's the same as the base, it's going to be 1. All right? So it's a little shortcut you don't need to remember. Now I'm going to throw a couple on there to see if you can follow. I'm going to step it up just a minute. Okay, try that. It's a little different. See what you get into. A little tricky. Hey, you guys, we shouldn't be touching our calculators. This could be a definitely no calculator deal. Okay? You cannot get an 8 with a whole power of 4. What does 8 and 4 have in common? What base do they both come from? Base 2. So I'm going to rewrite the 4 as 2 squared. And I'm going to rewrite the 8 as 2 to the 3rd. So the square still has the x attached. Now these guys are equal, so if the 2's are equal, then the exponents have to be equal. Okay, does that make sense? You want to break them down so they have the same base. As soon as the bases are the same, the exponents can be set equal and you're good. Make sense? Nothing too crazy hard. Okay. Try that. By the way, this lesson is not on your quiz on Monday. Just the first two. Because I made that decision yesterday after I wrote this. Okay, so hopefully you have 25 to the x equals the cube root of 5. 25 is a 5 squared. Cube root of 5 is 5 to the 1/3. What scares me is a lot of times this is the hardest part here. It's the last part. What does x equal? Yeah, 1/6. You're going to divide by that too, so it goes in up on the bottom. Okay? So can we do that? We're all happy? All right. Common logs are what your calculator LOG button is. It's base 10. Only for base 10. Okay? So you should be able to do some common logs. So if you do not see a base written, it's base 10. If they don't put a little baby number here, it is base 10. Just like if I write this, what do you guys say? That's the square root of 75, right? We don't actually put a 2 there. So it's an invisible 10. You're to assume it's there. So base 10, metric system basically, powers, scientific notation, whatever. What power do I have here if I've got 1, 2, 3, 4, 5, 6, 7 zeros? 7. So that equals 7. You're just counting place values when you're in base 10. So it's nice. So those are going to be easy to do. So let's try. Skip that. Here we go. What's this guy? 2. That's the kind of, we have to rewrite it. So this is 1/4. What's this guy? I'll rewrite it so you can see a little bit better back there. 1/1000. Negative what? 3. It's on the bottom. This is a special kind of rule. That's going to equal what? Just 6? This is in bin the log bunny form. Okay? If I want to write it logarithmically, so we have the log of the base equals the number equals log of 6. So it's going to equal 6. Okay? That's a special rule. All right? All right. I'm assuming you can pick your calculators up and type this in. We're not going to worry about that. Now, today's question. How do you solve when you're missing a piece? Okay? So, this one's missing the base. What is the base? Okay, so we know that's 10 because it wasn't written. So how do you find x? Write it exponentially. What's the base? And the exponent is 3. So x is 1,000. So to solve these, you're just going to rewrite it in another form. So what does x equal here? 2 to the 5th, which is 32. Okay. This guy here. 3 to the 1/2. Anytime you have that, the answer is probably going to be written as a square root or a radical of some sort. Okay. And the last one is 1/49. Now, you can solve for all 3 parts. These are all just solving for that x that's in the middle there. But if you wanted to do something like trying to think of what I'm going to actually do here. If you wrote that exponentially, you could solve it, yes? X to the 3rd equals 8, so x equals 2. Okay? Let's say it was something completely different here. Let's do x to the 1.43 equals 8, and I want to find x. How do you get rid of the 1.43? How do you get rid of an exponent? If you raise it to the reciprocal, that gets rid of it. That cancels the exponent. So x equals whatever weird number that's going to give us. Okay? All right. A couple more things, and then we're going to be done. Natural logs are base E. Common logs are base 10. So the ln in your calculator, it's base e, and you use PERT formula or whatever last year you did natural log. All the properties are the same, just a different base. Okay, same properties. So we're not going to go over that because you can type them in your calculator and you can type those in your calculator. This is just an example of how they're used. So when will I see this ever in my life? Base 10 logs are used in business. They are used in science a lot. Your pH scales are balanced or base 10. Your decibels are base 10. Your seismic activities with your Richter scales are base 10. So logs are used there a lot. If you are a coroner and you're dealing with dead bodies, estimating the time of death is base 10. All that kind of stuff. Okay, so logs are actually used a lot. Now, whether you're going to use it in your basket weaving or whatever career you're going into, I don't know. But they are used a lot in the real world. Okay, so anything that's base 10 can be solved with a logarithm, or other bases as well. Okay, we won't worry about doing this question. We'll do it tomorrow or Monday. Okay, that is it.